Hey, y'all, let's cover section 4.3. Using a scatter plot to investigate cricket chirp, the table shows the number of cricket chirps in 15 seconds for several different air temperatures in degrees Fahrenheit. Plot this data and determine whether the data appears to be linearly related. So I discussed this in class. I have a major issue with this table. The table is that shows along the x-axis, which is supposed to be our domain, that the cricket chirps determines the temperature. But in fact, temperature should be along the x-axis instead. Just know it's going to bother me. I may make some comments, but I'll keep it clean. All right, so we've got our chirps and then the temperature. The chirps, they're saying that the number of chirps, 44, decides the temperature is going to be 80.5 degrees. It's not, it's literally the other. Okay, I'm gonna stop. Plotting this data suggests that there may be a trend. Now, this would still be accurate. We can see from the trend in the data, the number of chirps increases as the temperature increases. The trend appears to be roughly linear. Yeah, of course, you can see that, and you know I can't draw a straight line. Thanks, Joe. That it roughly goes something like that. Okay, you've got a straight line, and I hate this pen. There we go. So that's definitely linear. It looks very linear, and it's also increasing. Because remember, we decide if it's increasing, decreasing, or constant. As you're moving from left to right, looking at the function, this one is clearly going up, so it's increasing. All right. Find a linear function that fits the data in the table by eyeballing a line that seems to fit. I didn't do this because there's no way I could have gotten this. What they did instead was they created a better line than what I did, and this I can use to where we've got 0, 30, and 50 looks to be about on 90. So if we have those two, so we've got 0 and 30 and 50 and 90. Those would be our two ordered pairs given if we just eyeball and drew a line for this. All right. So not my eyeballs, apparently. From this, we could create a function. To create a function given two ordered pairs, we need to find our slope, which is m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Okay. Label real quick, x1, y1, x2, y2. 90 minus 30. X sub 2 is 50 minus 0. 90 minus 30 is 60 over 50. 6 divided by 5, or I'm sorry, 60 divided by 50 is 1.2. So our slope would be 1.2. So we could have a function of 1.2 times what, it actually needs to be a C, and they're using temperature. So temperature, based on the chirps, is 1.2 chirps, but if there's no chirps at all, you're going to start off with a temperature of 30 degrees. So that is our y-intercept. But there's our function. All right. For any other question for this? Nope, that looks good. All right. Interpolation and extrapolation. Interpolation is anything that falls within the data set, within that realm. So if you come back over here, the domain is our chirps and the range is our temperatures. So anything that falls in between, what's our lowest chirp here? It looks to be about 18.5 and our highest is 44. So for chirps, any chirps that we get between 18.5 and 44 would be considered an interpolation. It's internal, so it's inside our data set. It's interpolation if it is inside the domain of our data set. Okay, so any numbers that land in between 18.5 and 44 are interpolation. If we get any numbers that are outside, even if it's just 18.4 or 18.444449 up to 44.00000 whatever, anything outside of the domain is going to be extrapolation. extrapolation is out of, well, you don't even need domain here, inside data set. Extrapolation is outside the data set. Okay. And that could be where I had the domain. It could be domain or range, which is why I didn't necessarily need to have that. Same thing for the range. We've got the lowest, it looks to be 52, makes sense. And then this should be our highest. So our temp, the range is from 52 to 80.5. So any temperature degrees between 52 including up to 80.5 including is going to be interpolation. And then anything that is outside like 51 or 81, those are extrapolation because they are not, this line that we've created is not necessarily a representation of that. We're assuming it is based on extrapolation. So looking at, again, the line, if it falls between here and here, which was our 18 to, what was it, 44, 18.5 to 44, anything in between there is going to be interpolation because it's inside the set. And then anything outside of it, we're assuming, so this was an assumption as well as this, that's accurate. It's extrapolation. Same thing for the range. So this comes over here and goes up to right about there. Anything inside this range is interpolation. If it's above it or below it, it's extrapolation. Okay, so there's a fine group that have to do with where our data set is for our scatter plot. All right. So the next question here is, I know we've already got it worked, but I want to do this one. I need a piece of paper. Okay. It asks us a question, and I'm going to ignore the solution and just look at the question. These two questions are, would predicting the table when crickets are chirping 30 times in 15 seconds be interpolation or extrapolation? Okay, so we need to look at when the crickets are chirping 30 times. So we need to look at our graph. The chirps 30 times is going to be inside our, between here and here. So of course, it's interpolation. The other question is, would predicting the number of cricket chirps will make it 40 degrees be interpolation or extrapolation? Well, did they want us to predict? Okay. So for 40, well, that's clearly below. That's clearly below the temperature. So anything that we say is strictly going to be extrapolation. Okay. So what would that temperature be? I'm just curious. So we could do both. Let's find this again. So for the 30, we've already got a function we've created. What would be the temperature for 30 chirps? This is how I would calculate this. 1.2 times 30 plus 30 is what I need to calculate. 1.2 times 30 plus 30 is 66. So the other thing you can check here is to make sure that the 66 falls within the range of the data set. So is 66 in between? Of course it is. So therefore, yes, it's interpolation. All right, let's look at the other one. They're wanting to know about 40 degrees. So if T of C is 1.2 C plus 30, then the temperature is 40 degrees, is 1.2 C plus 30. We're just going to solve for C, the number of chirps that we would have at 40 degrees. Subtract 30 from both. We get 10 is equal to 1.2 C. Divide both sides by 1.2. And we get how many chirps? 10 divided by 1.2 is 8.33 chirps. So saying that we're going to have, let's just say 8 chirps at 40 degrees. Well, is that interpolation or extrapolation, first of all? And chirps, 8 of them, oh gosh, yeah, it's right here. It is definitely extrapolation. The other thing it asks for both of these is, do they make sense? Well, if it's going to be interpolation, of course it's going to make sense. The only thing we need to question here is the extrapolation, because that's the ones that we're assuming that this part of the line and this part of the line, we're hoping that the information we gain from here, we can extend in both directions to do the extrapolation. We hope that's the case. However, at 40 degrees, we cannot be guaranteed that we're going to have 8 chirps. We don't know. We don't know. We're guessing. We're extrapolating that information. We're hoping that's the case. I believe, however, that crickets don't start chirping until a little bit warmer temperatures. Okay. All right. Interpolation, extrapolation. I do a little bit of craziness on that. Please feel free to read through that. I'm not going to read it to you. You're quite capable. Okay, calculator. This is where I wanted to get. This is what everyone needs here. All right. Oh, here it is. It tells us here. Crickets stop chirping altogether once you get below 50 degrees. That's kind of neat to know, isn't it? So let's work on putting the data from those chirps and temperature into our calculators. I am going to use a TI-84. The TI-83s or 81s, they all, I mean, I could use I've got an 83 as well. They're all treated the same way. The only people who are going to struggle, because I can't make one, is the Casio folks, or if you happen to use an HP or anything like that. If you have a TI, then you're good to go. These same directions will work no matter which one you have. All right. So the first thing I want to show you is to make sure your diagnostics are, well, we can do that in a minute. We can do that in a minute. Let's go look at our data and see if we have any data in here so we can clear it, so we can enter new stuff. Or you can go over the things that are already in there. Wrong one. The one I would want you to do is hit stat and hit enter just immediately. I have nothing in mine. I've got list 1 and 2 that I'm going to be using. That's the only 2 I'm going to be using for XY coordinates. That's all we're going to do in this class. So we're just going to go through and input the data for the L1 and L2. I'm not going to make you sit here and watch me do that. I'm going to pause the video, but I do want to show you so you can do the same thing along with me. Turn off my light. There. Oh, that's too much. Sorry. The light's too much also. So what you're going to do is you're going to put in L1, you're going to put the chirps. So go through and you'll go 44, enter, 35, enter, and just keep going until you get all the chirps in. Then you're going to hit your button to the right and click over. And you're going to enter your temperatures. So 80, they have to go in, match up 80.5, 70.5, and then keep doing that. I'm going to show you one more thing. If you've got data that goes past where the chirps and the temperature goes, and you want to clear your data, do not hit delete for these, but you can just scroll up and hit clear and enter, and it will clear it for you. If you hit delete, you're going to get rid of your L2. You don't want to do that. So just hit clear and enter. All you have to do is scroll up to make sure it's highlighted. Hit clear, which is right there, clear, and then notice it's got L2 is equal to blinking, hit enter, and it will clear it. Okay, that's it. I'm going to pause the video. Okay, once you get all of your data in, just leave it there. You can clear it, whatever you want to do. You can just quit. Second mode is quit. The next thing you're going to want to hit it anyways is stat. All right. And we're going to go one button over to calc. So you can just use your arrow button to move over to calc. And now we're going to go to the linear regression line, AX plus B. And this is number 4. You can scroll down or you can just hit 4 and it takes us straight to it. When you do that, it's going to show you what your X variable is representing, list 1, and your Y variable is being represented by list 2, just to make sure that that is entered correctly, which is why I wanted to verify that you're putting it in this way, even though it makes me angry that temperature is not the X variable. That's all we need to do. Hit enter, 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 1, 2, 3, 4, 5, until it hits calculate, and then it's going to populate this for you. Okay. If you did not get the R square and the R. I'll talk about that here in a second about how we can get that. The first thing I want you to see is that y equals ax plus b is the same thing as y equals mx plus b, to where a is your slope, and in this case it's 1.143175,185. And then your y-intercept, or when you're, is going to be 30.28058,507. This aligns really close to what we found using our sketched line that they had provided us. Remember, it was 1.2x plus 30. It's very similar. Okay, this is the numbers you would use to calculate the same way, but using the true linear regression or line of best fit. There is only one line of best fit. There is never more than one. Okay, so there's only one answer for this. The next thing I want to talk about is the correlation coefficient. If this did not populate the R square and R, I want to show you how to get that to populate for you when you do this, because you have to have that. And I'll be discussing more about that here in just a minute, but let's get your calculator to show you that number. All right. So all you have to do is, I'm going to just do a quick clear, go to second 0, where the catalog is. So second, let me show you the calculator, second, and then 0, and my catalog populated. I need to scroll down to diagnostics. There's a faster way. I haven't looked it up. It's not too bad though. All right, let's get to diagnostics. Okay, there's diagnostics off, which if you do not have the R square and R, you currently have highlighted. We need diagnostics on. So highlight that with your arrow and then just hit the enter key. Diagnostics on, hit enter again, and now it is done. Go back, test to make sure it works. Stat, calc, LenReg 4, or go down, and then just enter, enter, enter. And there you go. Okay. Mine were already on, so you're not going to notice a difference. Now I'm going to talk about the correlation coefficient. Keep going. If you have any questions up to this point, please make sure you write it down and you let me know. Oh, there's also some good stuff here as well. All right, so correlation coefficient. If your R, let's look at our R. If your R is greater than 0, so if it's positive, that means you're have an increasing relationship from the data. The data itself between your X and Y is increasing. If your R value is negative, ours is not, ours is positive, then you have a decreasing relationship. All right. It's going to also be in line with whether your line is increasing or decreasing. It's the same concept. Okay. The next piece of this is we want to evaluate what is our R representing. One, our R is representing that we're going to have an increasing relationship because it's positive. The other thing we can see is the closer the value is to 0, the more scattered the data. Ours looked pretty tight, so it wasn't very close to 0. But the further you get from 1 and -1, closer to 0, and I'll show you a little design I did for that, you'll see what I'm representing. The closer the value is to 1 or -1, the less scattered the data is. And I'll show you the words to use for this. Ours is really stinking close to 1. So this has got a really strong positive or increasing relationship. All right, so that's all you need to know about correlation coefficient as far as how to find it. I want to show you something that typically helps students in understanding. Let's go with 0, -1, and 1. All right, this is the range that you're going to have for your correlation coefficient. The closer the value is to 0, from -1 or from 1, the weaker and weaker, the more dispersed and scattered that the data will be. So this is there is no form whatsoever for this. So this is weak here. Now, weak is one thing, but is it increasing or decreasing? Increasing. So we have a weak increasing or decreasing relationship between the data. All right. If your data, if your R coefficient, correlation coefficient is really close to -1, then that's going to be strong. And because it's negative, it's going to be a strong decreasing relationship. If it is over here closer to 1, then it is going to be a strong, again, but increasing relationship. All right, hopefully that model helps you a little bit. I think I've got one more that I'm going to input. At least, yep. No, we looked at that one. There it is. All right, I wanted to do this, and I wanted to do this and use it the way I would use it on an exam. And I don't remember if I did this in class or not, because that was so pre-vacation or spring break. Gasoline consumption in the United States has been steadily increasing. Consumption data from 1994 to 2004 is shown in the table. Determine whether the trend is linear. If so, find a model. Put this here real quick. There we go. If so, find a model for the data. Use the model to predict the consumption in 2008. Okay, which is just a picture of it. So they've got it plotted already, what the line of best fit is. And you can already, one of the things I want to talk about the correlation coefficient is they're finding the average from the dot to the line, from the data point to the line. This other one over here, let's find the one, the distance between the point and the line, they take the average of each one and they calculate it for the correlation coefficient to where our line is giving us the best, truly the best fit. Okay. What's next? I want to enter this data. All right. So we'll put in the years for our X variables, because remember, time is X, and consumption of billions of gallons of gasoline is going to be, well, this needs more space. This should be a 3 here. The 3 should be up here. The 6 should be here. So please enter that into your calculator if you need help as far as clearing your calculator. Let's go back into stat and just hit enter for edit. And we can clear these lists. Again, do not hit the delete key. We're going to arrow up, make sure it's highlighted, and then hit clear and enter. Okay. Scroll over to list 1, tab up, make sure it's highlighted, hit clear and enter. You could also just type over the numbers that were in there, but sometimes there's more numbers than there are new data. So sometimes it's best just to clear it each time. All right, I'm going to go through and input this information, and I'm going to make sure that this is how the problem with this is I'm not going to put in 94 and 95 and 96, because that's not going to work when I put it in my data set, in my values. So instead, I'm going to have to use the number of years after 1994. So for the first one, we've got 0, because this is 1994. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So make sure for your X values, you put in 0 through 10, and then follow up with putting these numbers in afterwards. Again, the 3 goes here, the 6 goes here. I didn't create, I don't know what happened with my spacing, but let's go through and do that. I'm going to pause the video so you don't have to watch me do it. Okay, I've entered my data in for the years after after 1994, using 1994 as my 0. And then I've entered in my Y values in list 2 for my consumptions of billions of gallons of gasoline. All right, trying to see what else I wanted to make sure we got that covered. So let's go ahead and create our line of best fit. Let's do our linear regression. I can just go from here and just hit stat. I need to scroll over to calc. So arrow over to calc. I can hit 4, or I can scroll down and hit enter once I get to 4, which is the linear regression for line of best fit. We've already got our L1 and L2 set up. If it is not set up correctly already for you, go back up there. And I'm sorry I didn't say this initially. You can change your list Notice the L1, L2, L3, here's all of your lists located down here. To change this to L1, all you have to do is hit the second key and then 1 to make sure that's L1. All right, you'll do the same thing for L2. All right, and then calculate. It calculated that we have, let's write this down, y equals ax plus b. So y is 2.2091. We'll just go with that. X plus, we have a y-intercept of 113.3182. And then we've got a correlation coefficient that, my gosh, couldn't get much closer to 1 if it wanted to. And you can tell that it's positive, so it's an increasing relationship as well. So we've got a very strong increasing relationship between our data. So it's really good, a really good line that's been created. It's really tight on the points, which why I kind of had to jump to the other one, because there's not a lot of space in between these points and the line. It's just pretty nice. It's nice and tight. All right. So the next question I would ask you on an exam is to take your line of best fit, and you will all have the same exact answers for the line of best fit. I will tell you what to round these to, so that I can make sure that we all get the same answers. So whenever I make the video, it's consistent. So let's just say that we round this to, well, 4. I've already done that, so that's perfect. Make sure you round your numbers to the 4 as I did. This is a 2. All right. And I want to know, well, let's just talk about one more thing real quick. What if I wanted to know, without looking up here at my data set, what the value is? Pretend like I don't have my data set available. What the consumption of gas was in, let's see, it was 5, 6, 7, 8, 9, 9, in 2000. So what is the consumption of gasoline in 2000? Well, I know that 0 is 1994. So I would come over here, 94, 95, 96, 97, 98, 99, 2000. What was the consumption of gasoline at that time? Well, it's right there. But what is it exactly? I can find out exactly what it is by taking the 6 and substituting, because this is a f of, what is this? Gas consumption, so G of Y, G of T probably. So let's go with gas based on time. So that's 2.2091 T plus 113.3182. All right, and I want to know in the year 2000, without looking at my numbers up here, pretend like we don't have them, what is the gas consumption? All right, in billions of gallons. So I have to use the number 6, because I'm not going to plug in 2000 for my T. I'm going to put in 6 for my T and solve. 2.2091 times 6 plus 113.3182. All right, let's do a little calculation here. 2.2091 times 6, and I know I didn't do this in class, plus 113.3182, but it's stuff that's really important. And I get that 126.5728 billions of gallons of gasoline, billions of gallons of gas was consumed in the year 2000. So I'm curious if we're close to the data set, because I'm not even referencing that yet. So let's go over here and see what 2000 was. 126. Pretty good. Pretty good, pretty good, pretty good. So if this is accurate, and this is a close guesstimate, it's pretty good. So what if I wanted to know what year, let's go with this. What year, this would be the other question I'd ask. What year did the consumption reach, what can we say? How about 128? No, 120, let's go with 4. Reach 124, and that would be billions of gallons of gasoline. Billions of gallons of gas. That would be the next question I would ask on this. So 124 is right about here. So, oh, my lines. And that hits, well, we know it's going to be before 2000. All right, so let's see when that happens. To find out when that happens, I'm going to take the 124 and substitute it instead for my G of T. Let me rewrite it real quick, 2.2091 T plus 113.3182. I'm going to substitute for my G of T, the 124, plus 113.3182. And I'm going to solve for T. So I'm going to take the 124, subtract 113.3182. Oh gosh, too many. So that's subtracting 113.3182 from both sides. And we're left with 10.6818 is equal to 2.2091 T. Now we're still solving for T, so I have to divide both sides by 2.2091. That's a 2. So divide by 2.2091, and I get 4.835. Do I need any of those decimals? Well, let's see. Let's see what years it's falling in between, and we can have that discussion. So this number is being represented by a 4 point blah, 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 but it's what it truly is the number of years after 1994. So that's taking 1994 and adding, let's just say we add 4.8. Does that matter? Are we going to say that it happened and that we consumed 124 billion gallons of gasoline in the year 1998.8? No, we're not going to say that. No, we're going to say, and we're not going to say 89 either, or 99 either, because we're not there yet. This isn't 1999. You don't round up. It hasn't happened. So you're just going to say it happened in 1998. Okay. What I just showed you is what I would do for an exam or for your quiz to ask you to utilize your line of best fit to solve, also to represent what your correlation coefficient is as well. All right. Let me know if you have any questions.